Good day, everyone. We're diving into the fascinating world of AI with our presentation titled Fine-Tuning Large Vision Language Models as Decision-Making Agents via Reinforcement Learning. We'll explore how we can enhance the decision-making capabilities of these models in interactive environments using reinforcement learning. Stay tuned for a deep dive into our innovative approach and its promising results. Let's get started. Large vision language models, or VLMs, have shown remarkable potential in language reasoning tasks. However, when it comes to training these models for multi-step interactive environments, the current methods fall short. Reinforcement learning, or RL, could be a promising solution to this problem, but its application in fine-tuning VLMs is still a relatively uncharted territory. Now, let's delve into the problem statement. Existing RL methods often lack visual inputs, which limits their applicability to tasks that require a combination of vision and language understanding. Furthermore, the impact of chain of thought, or COT reasoning, on RL training in large models is yet to be explored. This leaves us with a significant gap in our understanding and a compelling area for further research. The crux of this research lies in the proposition of a reinforcement learning-based framework for fine-tuning large vision language models, or VLMs. This framework guides the VLM to generate task-specific chain-of-thought reasoning, which then leads to a text-based action. These text-based actions are then parsed into executable actions that can interact with the environment. Moving on to the evaluation and results, the proposed method was put to the test on a 7B model across 5 decision-making tasks. The results were quite promising. The method not only enhanced the decision-making capabilities of the VLMs, but also outperformed commercial models like GPT-4V and Gemini. This demonstrates the potential of this approach in improving the performance of VLMs in decision-making tasks. Large vision language models, or VLMs, have shown remarkable potential in solving a variety of tasks through language reasoning. However, there's a challenge when it comes to training these models for decision-making in multi-step interactive environments. This is because the traditional method of visual instruction tuning may not cover a wide range of decision-making scenarios. To address this, we propose a reinforcement learning, or RL, fine-tuning framework for VLMs. As illustrated in the diagram, the state at each time step contains an input prompt and a visual observation. The VLM takes these as input and outputs open-ended text containing the chain of thought reasoning, keywords action, and the log likelihood of the output. A post-processing function is then applied to obtain a legal action which can interact with the environment. The action is input to the environment to obtain a reward and the next observation. We then compute a numerical value of the action probability, which is used for RL training. This approach allows us to enhance the decision-making capabilities of VLMs in interactive environments. As we delve into the world of large vision language models, or VLMs, we find that fine-tuning these models with specialized visual instruction is a common practice. However, this approach may not be the most effective for multi-step interactive environments. Why is that? Well, visual instruction tuning relies heavily on supervised learning from pre-collected datasets, without any interaction with the environment. This could pose a problem if the datasets lack diversity, potentially hindering the improvement of the VLM's decision-making capabilities. So, what could be the solution? Enter reinforcement learning, or RL. This method offers a promising paradigm for training decision-making agents in multi-step interactive environments. However, there's a gap in the research here. The end-to-end fine-tuning of VLMs with RL for goal-directed multi-step tasks is an area that hasn't been thoroughly explored yet. This is where our research comes in, aiming to bridge this gap and enhance the capabilities of VLMs. Our research presents a novel algorithmic framework that directly fine-tunes vision language models, or VLMs, using reinforcement learning for multi-step, goal-directed decision-making tasks. Here's how it works. The VLM first receives a task description prompt. This guides the model to generate task-specific chain-of-thought reasoning, followed by a text-based action. Why is this important? while enhancing the decision-making capabilities of VLMs in multi-step interactive environments is a crucial step forward in AI advancement. Previous solutions fell short as they did not incorporate visual inputs or chain-of-thought reasoning. Moreover, they did not allow VLMs to directly interact with environments using open-ended text. Our approach addresses these gaps, offering a more comprehensive solution for training decision-making agents. Our research introduces a novel algorithmic framework that fine-tunes vision language models, or VLMs, using reinforcement learning, or RL. This process begins with the VLM receiving a task description prompt. The VLM then generates task-specific chain-of-thought reasoning, which leads to a text-based action. This action is not the end of the process, however. We parse these text-based actions into executable actions that the environment can understand. This interaction with the environment generates rewards and the next state for RL training. This innovative approach allows us to enhance the decision-making capabilities of VLMs in multi-step, goal-directed tasks requiring vision language understanding. Our research proposes a novel method to enhance the decision-making capabilities of large vision language models. Here's how it works. First, the VLM policy generates open-ended text, not the typical vectorized actions. This allows for more nuanced and complex responses. Next, we design a task-specific prompt. This guides the VLM to generate a formatted output, which includes chain-of-thought reasoning. This reasoning is crucial for efficient exploration and decision-making. We then use a post-processing function to parse this open-ended text into a legal action. This action can directly interact with the environment. To estimate the action probability, we've developed a method that considers the probability of each output token. This ensures that the action is not only possible, but also likely to be successful. Once we have our legal action, we input it into the environment. This allows us to obtain a reward and the next observation, which are crucial for reinforcement learning training. Finally, we compute a numerical value of the action probability. This value is then used for reinforcement learning training, helping the model to learn and improve over time. In essence, our method combines the strengths of VLMs with reinforcement learning, offering a promising approach to improving decision-making in multi-step tasks. Our research takes a unique approach compared to previous methods. Firstly, we incorporate visual inputs into our model, expanding its applicability to tasks that require a combination of vision and language understanding, or what we call multimodal reasoning. This is a significant step forward in the field, as it allows our model to handle a wider range of tasks. Secondly, we explore the impact of what we term as chain of thought or COT reasoning on reinforcement learning training in large models. This is a novel concept that prompts the model to generate intermediate reasoning steps, leading to the final decision, enhancing the efficiency of exploration. Lastly, we enable vision language models, or VLMs, to directly interact with their environments using open-ended text. This is a departure from traditional methods that use vectorized actions, and it allows for a more natural and intuitive interaction between the model and its environment. In essence, our research pushes the boundaries of what's possible in the realm of VLMs, opening up new possibilities for their application and performance. Our method was applied to a 7B model and rigorously tested across 5 decision-making tasks, spanning 2 distinct domains. The empirical results were quite promising. They showed that our approach significantly enhances the decision-making capabilities of vision language models, even outperforming commercial models such as GPT-4V and Gemini. But perhaps the most exciting finding was the pivotal role of chain-of-thought reasoning in reinforcement learning training. This highlights the untapped potential of VLMs as decision-making agents in interactive environments. So, as we delve deeper into this field, we can look forward to more breakthroughs in the use of VLMs for decision-making tasks. Our results underscore the effectiveness of reinforcement learning in fine-tuning large vision language models for multi-step, goal-directed decision-making tasks. We found that the integration of visual inputs and chain-of-thought reasoning significantly bolsters the performance of reinforcement learning training. This approach allows these models to interact directly with their environments using open-ended text, thereby enhancing their decision-making capabilities. To further validate our approach, we conducted an ablation study, specifically examining the role of chain-of-thought reasoning in reinforcement learning training. The results were clear. Without chain-of-thought reasoning, we observed a significant drop in performance across both domains. This underscores the critical role of this reasoning process in our reinforcement learning training framework. As we draw conclusions from our research, let's revisit the key contributions we've made. We've developed an algorithmic framework that fine-tunes vision language models with reinforcement learning for multi-step, goal-directed decision-making tasks. This framework is unique in its use of chain-of-thought reasoning, a crucial element in our RL training for VLMs. Take a look at the figure displayed. It shows the training curves of our method with and without the CoT reasoning across various tasks. You can clearly see a significant drop in performance when CoT reasoning is not incorporated, underscoring its importance in our RL training. Finally, we've demonstrated that our proposed method enhances the decision-making capabilities of VLMs in both original and embodied AI domains. This is a significant step forward in the field, and we're excited about the potential applications of our work.